Alright, thanks for watching. And today I will finally show you why it's true that gamma of x times gamma of 1 minus x is pi over sine of pi x. And by the way, this formula also holds for complex numbers. So if x is complex, but today, because the proof is so nice, I will do the real case. And by the way, again, I would like to credit Herman Jaramillo for this. It's a great proof. And also, the proof I'll present is for x between 0 and 1. And at some point, that will be important. Well, again, in general, this is true for complex numbers, but the proof is beyond the scope of this video. Okay. And you'll see it involves complex residue calculation, so complex integration. And it's one of the hardest complex integrations I've seen, so brace yourselves. Alright, and this fact, notice it looks a bit like the beta function, so we have to use one little fact that I've shown, I think in a video about sine of x squared. It's true that gamma of x times gamma of y, it's the same as beta of x comma y over gamma of x plus y, where the beta function, and there are again many formulations of this, today I will use this formulation, integral from 0 to infinity of t to the x minus 1 to the 1 plus t x plus y dt. Okay, and in particular, let's see what happens in our calculation. So in this case, gamma of x times gamma of 1 minus x then becomes beta of x of 1 minus x comma 1 minus x over gamma of 1, because you see the sum of those two is 1, and gamma of 1 is the same as 0 factorial, and that's 1. So the point is, in order to prove our formula, it is enough to show that this beta function equals to what we want. So enough to show that beta of x, 1 minus x, equals to pi over sine of pi x. In other words, we have to show that the integral here from 0 to infinity of t to the x over 1 plus t to the x plus 1 minus x dt is equal to this thing. But you see, the integral simplifies nicely because this x, the x's cancel out, and you're left with integral. Let me write this on new part here. So we have to show that the integral from 0 to infinity of t to the x over 1 plus t dt equals to pi over sine of pi x. Okay. This is really our goal for today. And we'll do that using a complex integration. So in this case, consider the function f of z, which is, I forgot the minus 1 here. So I want to show that t to the x minus 1 over 1 plus t is this. So now let's consider the function f, which is z to the x minus 1 over 1 plus z. So remember, x is fixed, and we're integrating with respect to t, so we want to figure out this f here. So in other words, we replace t by z, so we want to consider this complex function f, and we want to integrate it on a very complicated path. And let me explain you how to get it. So here's maybe step 2. Okay. notice this function has a singularity at -1, and in fact it's a very mild singularity. It's one of those residues that will help us. So here we have -1, but also remember that x is between 0 and 1, so we also have a singularity at 0. But this one, the singularity at 0, is a very bad singularity, and we want to avoid this. So somehow we want to integrate around this 0 by avoiding this. But also we really want this -1, so we want some contour which takes this -1 into account, but also, of course, so that we get a real integral. So what we really want is really this keyhole integral, this huge thing here, that goes like that, goes like that. It's sort of a Pac-Man-y integral, but not quite. It's like more a dinosaur integral, because Pac-Man is more the triangle one. And I will, explain the terms, exactly what we want, but the point is here we have a huge number, r ei theta. Here we have a small number, epsilon ei theta. And the point is this is the real axis, so we want something that's as close to the real axis as we want. And as I said, I will define the terms more precisely later. But of course, notice there are four features to our path or contour. There's first this path A, which will give us a real integral. There's a path B, which we hope goes to 0 as r goes very large. There's a path C, which gives us our integral, a real integral, but maybe there's some weird constant. We'll talk about this later. And lastly, there's a part D, which again we also hope goes to 0. And therefore, the integral of f is just, the sum of those four integrals. The point is, I guess the integral of f over that contour, so let's call it I, is just the sum of the four integrals, a plus b plus c plus d, right, of f of z dz. Good, now we have a complex analysis problem, so let's do that. All right, now we want to do a residue calculation, so let's study the whole integral at first. Let's do step 3. Study of the integral I, and remember our function is f of z is z to the x minus 1 over z plus 1. And you see there are two singularities, the 0 and minus 1, but in our path we don't have the 0 point anymore. So what's left is really just the residue at minus 1. So by this Cauchy formula or something, we get I is 2 pi I times the residue at z equals to minus 1 of f of z. But if we just have, I guess a pole of order 1, it's not too bad to calculate the residues. It's just equal to 2 pi I times limit as z goes to minus 1 of this times the z plus 1. So z minus the singularity times f of z, which here becomes 2 pi I times the limit as z goes to minus 1 of z to the x minus 1. Okay, I really don't want to erase that picture, but we have 2 pi I times minus 1 to the x minus 1. However, again, remember x is between 0 and 1, so you're technically taking a root of a negative number, and to avoid, I guess, to make this more explicit, that's 2 pi I e to the, I guess, pi I. E pi I is minus 1 times x minus 1, and then let's just leave it like that. That's enough to simplify this. Okay, so we indeed get that the whole thing, if you integrate the whole contour, you get this thing, 2 pi I times this complex number, so a very strange complex number. And now, let's focus on maybe let's do the easy parts first. So let's first do the small part and the huge part. Well, maybe now let's maybe erase the picture and do something more explicit. So let's study D. I guess step 4 of D. Now D is this contour here, right? So you start, I guess, let me see. You start here and you integrating here. And what you want to do, this contour depends on a small parameter epsilon, and it's really the contour epsilon ei theta, where theta ranges between an angle gamma here. So this is, I guess, epsilon ei gamma. Sorry, delta, sorry about that. So the endpoint is delta, and I want to say the beginning angle is minus delta. It's just there's this weird thing about, because we're taking sort of logarithms, this is an explicit, logarithm, and the thing is with logarithms there's this multi-valuedness, and we have to take a branch of log, which means that our angle, it has to be in the same multiple of 2 pi, and because we're in the same multiple of 2 pi, we have to take it from delta to epsilon ei 2 pi minus delta. So again, it's a very confusing point. I'm personally confused by it as well. But if you want to take a branch of the logarithm, which we'll do later on, we have to choose the angles between delta and 2 pi minus delta. So let's choose this path. Gamma of t equals to epsilon ei of something. And what that something to be start at gamma and end at 2 pi minus gamma. Because again, we want the time to be increasing, and that's why it's good to choose 2 pi minus t. Because notice, at gamma, it starts at ei 2 pi minus gamma, and it ends at ei 2 pi minus 2 pi minus gamma, which is precisely ei to the gamma. But notice, we can actually change this into epsilon ei of 2 pi, times e to the I of minus t, and that's just 1, so epsilon e to the I minus t. And its derivative, right, becomes epsilon minus I e to the I of minus t. All right, very good. And now we can just plug it into a formula. So, and by the way, like delta, this angle delta here, it depends on epsilon. So there's probably an explicit formula for it, but we don't really care about this. But the important property is delta, as epsilon goes to 0, it also goes to 0. And we'll use that in a second. So the integral over d of f of z, dz, becomes the integral from delta to 2 pi minus delta of, again, now, what is f of z again? F of z is z to the x minus 1 over z plus 1. And therefore we have gamma of t to the x minus 1 over gamma of t plus 1 times gamma prime of t dt. Well, that's equal to integral of from delta to 2 pi minus delta of, so gamma is epsilon to the x minus 1 e to the I of minus, e to the I of minus t to the x minus 1 over epsilon e to the I of minus t plus 1 times the derivative, so epsilon of minus I e to the I of minus t dt. Right? Some pretty scary stuff, but it turns out there's a really nice, even though this is a very scary integral, we want to show that it goes to 0, so we just need to take absolute values everywhere. So absolute value, absolute value, absolute value. And then let's use a triangle inequality. So that's less than or equal to integral from delta to 2 pi minus delta. Absolute value, so epsilon to the x minus 1, absolute value of e to the I minus t to the x minus 1, but e to the I real is 1, so this is 1, over epsilon e to the I minus t plus 1, and then absolute value of epsilon, absolute value of minus 1, absolute value of e to the I minus t dt, well that's 1, that's epsilon. Okay. Alright, now what about this sucker? Well, we want to show that 1 over this quantity is less than or equal to something, so it would be nice to show that this quantity is greater or equal to something, but for this, we use an equality that's never useful, except for this case, which is called the reverse triangle inequality. So usually the triangle inequality tells us that stuff is less than or equal to something. The reverse one tells us that it's greater or equal to something. And as I said, it's one thing that you really like to use, but it's completely useless because it never gives you more information, except here, because if you like here, A is this, and B is minus 1. So this is greater or equal to absolute value of epsilon e to the I minus t minus absolute value of minus 1, which is greater or equal to, equal to epsilon times 1, and then minus 1. But, of course, epsilon is close to 0, so epsilon minus 1 is negative, and you're left with 1 minus epsilon, which tells us that 1 over this value is less than or equal, so 1 over epsilon blah 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 is less than or equal to 1 over 1 minus epsilon. Okay. So we have deconstructed this integral, so now let's put all the terms together. Now everyone together, let's do it. To the left, okay. So now the integral over d in absolute values is less than or equal to integral from delta to 2 pi minus delta of, okay, so we have epsilon to the x minus 1, there's this extra factor of epsilon, and it's less than or equal to 1 over 1 minus epsilon, so dx, or dt, whatever we use, yeah, dt, and that is, conveniently, epsilon to the x over 1 minus epsilon, integral from delta to 2 pi minus delta dt. And here's the cool thing. The exponents work precisely so that this is true. So if we had epsilon x minus 1, this would blow up. But remember that x is between 0 and 1. So in fact, as epsilon goes to 0, this goes to 0, and well, this is 2 pi minus delta. And now, as epsilon goes to 0, remember I told you that delta also goes to 0. So no matter what its exact value is, it goes to 0. So we have something that is 0 times 2 pi. So as epsilon goes to 0, this integral actually goes to 0. Whew. 1 out of the 4 is done, okay? And now we want to do the same spiel, but with the big circle. Well, I think the big one is a bit easier. We don't have to worry about minuses or anything. Okay. All right. So this is step 5. So study of B. Again, here what we want to do, we want to integrate over this big circle. So r ei theta. And same as before, we want to start with some angle. So r ei delta prime. And we want to integrate up to r ei 2 pi minus delta prime. So in the picture, the thing is symmetric, so it should be minus delta prime, but again, there's this thing about this branch cut that forces us to choose 2 pi minus delta prime. And again, even though we do not know what delta prime is, we know that delta prime, it goes to 0 as r goes to infinity. Because if the radius is very big, the angles, they approach 0. So very good. And so here, it turns out the parametrization is even easier. Gamma of t is r eit, where t is between gamma prime and 2 pi minus gamma prime. Sorry, t is between delta prime and 2 pi minus delta prime. And so the derivative here becomes ri eit. And so let's calculate the integral of f over b. So we get integral of f dz that's equal to integral from delta prime to 2 pi minus delta prime of, again, what's the function again? Z to the x minus 1, so gamma t to the x minus 1 over t plus 1, gamma prime t dt, that equals to the integral of delta prime of 2 pi minus delta prime of ri e to the it to the x minus 1 over, sorry, that's gamma t of ri e to the it plus 1. Man, what's wrong with me? So that's, sorry, r e to the it. So just our gamma, and then we have ri e to the it dt. And again, horrible thing, but we want to show it goes to 0. So let's take absolute values. And then, so this is less than or equal to delta prime, 2 pi minus delta prime. And then, so r to the x minus 1. E to the it in absolute value, it becomes 1. So we ignore it. R is r. Absolute value of this is 1. So dt over r e to the it plus 1 in absolute values. And now, again, let's use the reverse triangle inequality and solve this. So r e to the it plus 1 is equal to r e to the it minus 1. And let's reverse triangle inequality this. So r e to the it minus absolute value of -1, and that's absolute value of r minus 1. But r goes here in, it's ginormous, so you get r minus 1, and so 1 over the absolute value is less or equal to 1 over r minus 1. So the integral of b of f is less than or equal to integral over delta prime 2 pi minus delta prime r to the x over r minus 1 dt, and that's r to the x over r minus 1 times, so 2 pi minus delta prime minus delta prime. Again, as r goes to infinity, this goes to 0, so the angle goes to 0. So the whole thing goes to 2 pi. Now, what about this thing? The problem is we have infinity over infinity, and do. This calls again for the L'Hopital. Okay? So, limit as r goes to infinity of r to the x over r minus 1, that equals to, by L'Hopital's rule, limit r goes to infinity of x to the r to the x minus 1 over 1. Again, x is just a constant between 0 and 1. And so r to the x minus 1 is 1 over r to a positive number. So the point is, this is x times 0 over 1, and that goes to 0. So in other words, as r goes to infinity, this goes to 0, and in particular, the whole integral goes to 0. Whew. Okay, that was the easy part. Wow. Okay, now let's do the actual contributions. So it's cool, like between the two, the 4 contributions, the circle thingy give you 0, and now let's do the actual thingies. So let's say with the upper part first, if you want. So step 6. Let's now study A. So what is A? Remember, we started with this point, epsilon EI delta, okay, and it goes to the beginning of the upper circle, which is R EI delta prime. And so I know I was a bit vague about what the values are, and I'm still going to be vague, but the thing is, this is a horizontal line, so it will be the beginning point is equal to A plus CI, and the final point is B plus CI. And again, we don't really know what A and B are, or C, but what we do know is that the height of those 2 points is the same. Okay? So in particular, we can still do a nice parametrization. In other words, what is gamma of t? Well, it's just A plus T plus Ci. Because you start at A. If you start at A, you get A plus Ci. If you finish at B, you get B plus Ci. So this does work. So in other words, also gamma prime of t is 1, which tells us it's good. We don't have to worry about the derivative term. So the integral of A over A is integral from A to B of gamma t to the x minus 1 over gamma t plus 1, gamma prime dt, but gamma prime is 1. So we have that. And then that's equal to integral from A to B of t plus ci to the x minus 1 over t plus ci plus 1 dt. Okay, and here is where we want to be a little bit careful, I think, because what we want to do first is we want to let r go to infinity. So if r goes to infinity, again, super important, I'm first letting r go to infinity. If r goes to infinity, it doesn't really affect the c. It still stays the same. So we're left with integral from t plus ci x minus 1 over t plus ci plus 1 dt. The only thing I think that really changes is that b goes to infinity. So we have integral from h to infinity of that. Alright, I think now what's happening, now it's the important thing. We have this point, epsilon ei delta, which is a plus ci. We have the other point, which just vanishes. If you have the origin, this is sort of your height c. Okay? And I guess this is your a, if you want. So it's sort of, you get a unit to the right and c units up. But look, now, if you let epsilon goes to 0, then a goes to 0 and also c goes to 0. So now if epsilon goes to 0, you indeed get the integral from 0 to infinity of t to the x minus 1 over t plus 1 dt. And here it's this complicated thing about residues, but branch cuts. I think here, because you have a positive t and a positive c, you're still in the point where you take this correct logarithm. So in fact, it goes to this integral as well. The point is, this is the harmless integral. So this equals to I. It's the next integral that's a bit complicated. All right. So brace yourselves, because now we want to study C. Let's see. I'm doubting myself, so okay, let's see if that works. All right. So step 7, the penultimate step. So study of C. And remember, how do you get this? So you started with A, B, and now you have this part. This is the part C. So how do you start with C? You start with R, EI, 2 pi minus gamma prime, and minus delta prime. I don't know. Keep screwing this up. Okay. And then you go to epsilon, EI, 2 pi minus delta. So this is your path C, if you want. And well, same as before, right? Even though we don't really know what those points are, we do know that the height of those 2 points is the same. So let's write this as A minus Ci, and then B minus Ci, where here C is positive. So we are slightly below the real axis. Because remember, epsilon r goes to infinity, epsilon goes to 0. And so one parametrization we can guess, we want to start at b minus ci, and we want to end at a minus ci. So how about, here, let's do something slightly different from the previous one, because here let's start with a path that goes from 0 to b minus a. Again, we're kind of reversing the orientation. So you want something where at 0 you're at b minus ci, and at b minus a you're at a minus ci, and the thing that works here is b minus ci. So you start here, and you do minus t. Because at 0 you get b minus ci, at b minus a you get a minus b, which cancels out, and you get a minus ci. And therefore, here I guess the derivative is minus 1. So the integral over c becomes the integral from 0 to b minus a of b minus ci minus t to the x minus 1 over b minus ci minus t plus 1 to the minus dt. Here comes the slightly confusing part. So, I'm still breaking white chalk, by the way, even though I'm not using it. But it's on the ground now. Okay, suppose here it's 0, and here it's our line here, right? So if we have gamma t is, b minus ci minus d. So on this picture, you see that the radius is large, but the angle is very small. So gamma of t, what it really is, it's some radius times ei times minus some small angle. But remember this thing where we said we don't really have minus delta, we want to have 2 pi minus something. So that's really radius times e to the I 2 pi minus small angle. All right, because again, it's fine because ei 2 pi, that's 1. And now let's see how we can simplify this formula here, because it turns out we have this negative number to the x minus 1, which gives you a very strange logarithm. And here's where the logarithm appears. So b to the minus ci minus t to the x minus 1. What this really is, it's e to the, this number, it's e to the ln of b minus ci minus t to the x minus 1, which becomes the following. So that is e to the ln of b minus ci minus t times x minus 1. But again, what do we have? Based on this thing here, we have that gamma t, which is b minus ci minus t, that equals to the radius times e to the 2 pi minus small angle. And the radius, well, it's really the modulus of this number. So b minus ci minus t times ei 2 pi minus some small angle. Okay, so we're not really worried about this much. And in particular, what we have here is that if we take ln's, so ln of b minus ci minus t, that's ln of this whole thing, so b minus ci minus t, e to the I 2 pi minus small. Well, that's really equal to ln of b minus ci minus t plus ln of ei 2 pi minus small. Treat the argument if you want. Okay, and here is where it said we have to use the branch cut, because this thing is still fine, ln of modulus t. But this thing, because we chose sort of the right range, between 0 and 2 pi, we can really say that this is the same as I 2 pi minus small angle. So once we have that, we can plug it into this formula. So we get that this thing, gamma of t to the x minus 1 becomes e to the ln of b minus ci minus t times plus I times 2 pi minus small, so I 2 pi minus I minus small. No, it's very physicist notation-y, but it's okay. And this times x minus 1. Okay. Right? And now, so if you'd like, now how about at this point, let's already send epsilon go to 0. So, and we could also let r goes to infinity later on, but that's fine. But now, let epsilon goes to 0. As if epsilon goes to 0, remember that c goes to 0. So you have this point here, maybe we have this point here. So epsilon e to the 2 pi I. So I 2 pi minus gamma. And this is compared to 0. And then we have this line here. And so remember, this is our point A. This is our point minus C. If epsilon goes to 0, then C goes to 0. And so epsilon goes to 0. So C goes to 0, and you're left with e to the ln of absolute value of b minus t plus I 2 pi. And then more importantly, as epsilon goes to 0, the angle here, so this is the small angle, I guess here maybe. This is the small angle. Well, as epsilon goes to 0, the angle also goes to 0. So you're left with really ei 2 pi, and the whole thing times x minus 1. And so what this really is, that equals to e to the ln of b minus t times x minus 1, and then e to the I 2 pi times x minus 1. And then you're really left with b minus t to the x minus 1, e to the I 2 pi to the x minus 1. This whole explanation to show you that when we do this integral on the below side, on the lower half, we actually get this extra factor ei 2 pi to the x minus 1 coming up. And that's again because you chose this angle 2 pi minus delta. You have to be in this range, 2 pi minus small angle. And we do have this extra thing popping up. And again, if you know branch cuts, it apparently follows from the choice of the branch cut here. Okay, good. So we have this, and then let's talk about our integral again. So, maybe here. What was our integral of c? C equals integral over c. That's equals to integral from 0 to b minus a, b minus ci minus t to the x minus 1 over b minus ci minus t plus 1 minus dt. And remember, at this point here, I let epsilon goes to 0. And remember, as epsilon goes to 0, we have both a goes to 0 and c goes to 0. So you're left with integral from 0 to b minus 0 of, again, this extra weird factor that pops up. So b minus t to the x minus 1 and b minus t to the x minus 1 times ei 2 pi to the x minus 1. And then the bottom, remember, c goes to 0, so you have b minus t plus 1, and we still have the minus dt. Notice in this region, t is between 0 and b, so you can actually remove the absolute value. So we're good here. And then, I believe, no, unfortunately not. We still have the t going on here. And well, ideally, we would like, b goes to infinity. But first, let's do a change of variables. So let u be b minus t, okay, and then du is in fact minus dt, so that's very nice, and then u of 0 is b, u of b is 0, so you have integral from b to 0 of u to the x minus 1 ei 2 pi to the x minus 1 over u plus 1, and then minus dt is du. And now, if you want, the interior doesn't depend on b, so now we can let r go to infinity. And we get the integral from infinity to 0 of u to the x minus 1 ei 2 pi to the x minus 1 over u plus 1 du. And look, it's basically equal to the integral we want because this thing doesn't depend on u. So you have e to the I 2 pi to the x minus 1 integral, I guess minus integral from 0 to infinity of u to the x minus 1 over u plus 1 du. But notice this is precisely minus our answer, so it becomes minus e to the 2 pi I x minus 1 times I. Okay, and so now we have done we have beaten the 4 bosses, and now let's move on to the final boss, to the Ganondorf of, I guess, Ganon of this complex analysis adventure. So now let's just put everything together. So step 8, epic conclusion. So what do we have? We have on the one hand, we have the residue calculation. And we found that the residues give you 2 pi I e to the I pi x minus 1. That's what we got from the residues. And then, from the integral calculation, everything blows up except our integral I and the contribution from the lower half minus e to the 2 pi I to the x minus 1 I, which is the same as I to the 1 minus e to the 2 pi I x minus 1. And therefore, our integral that we want is 2 pi I e to the I pi x minus 1. Now I'm hungry for pi. Okay, 1 minus e to the 2 pi I x minus 1. And then we can almost transform it to what we want. So here, how about, let's factor out e to the I pi x from both sides. So e to the I pi x minus 1, e to the minus I pi x minus 1 minus e to the I pi x minus 1. This nicely cancels out. And then how about we divide both sides by 2i. So that's equals to 2 pi I over 2i over e to the minus I pi x minus 1 minus I e to the I pi x minus 1, I guess, over 2i. And then, yeah. And you may recognize this. Remember, we have this formula, e to the I theta minus e to the minus I theta over 2i equals to sine of theta. Well, it's the same thing, but with theta equals to, I guess, minus, let's see, minus pi times x minus 1. And so what we're left with is, this is pi over sine of minus x minus 1 pi. And you might say, oh no, this is not quite our answer. Well, wait for it, because this equals to, so if you want, minus sine of x minus 1 pi, and that's minus sine of pi x minus pi, and that's minus sine of pi x, cosine of minus pi, and then plus, I guess with the minus, so minus sine cosine of pi x, sine of minus pi, but that goes to 0, and then cosine of minus pi is minus 1, so indeed, this weird thing is in fact equal to sine of pi x, so you're left with pi over sine of pi x. And coming back to the very beginning, what is I? I was exactly what we had here, the gamma function. So gamma of x times gamma of 1 minus x was the beta function, but we showed that the beta function equals to this one. And therefore, in the end, we do have gamma of x times gamma of 1 minus x is pi over sine of pi x. Well, congratulations on surviving this with me, and then, I'm very proud of you. It was very difficult. Alright, so if you like that and you want to see more math fun, please make sure to subscribe to my channel. Thank you very much.